You are responsible for completing 2 different activity manual activities for 11-2. We're going to just kind of talk through the completed version of the first one, and then we will work through the second one much more together. If you haven't already taken taken a chance at this first activity manual, pages 197 through 199, I want you to do that now. And then come back and we will just kind of talk through the key. For this, instead of rolling a die or drawing a card, we're tossing a coin. Assuming it's a fair coin, a coin is going to have 2 sides, heads and tails. If I'm flipping 2 of those coins, then I have 4 different ways the outcomes can come out. Either I can have I can flip heads on the first coin, which means the second coin could be heads or tails, and I get heads, 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 tails as those 2 outcomes. Or I could get tails on the first coin and get heads or tails on the second. So I either get heads, tails, heads, heads, or tails, heads, tails, tails. And you could think about them as 2 separate coins, or maybe even flipping the same coin twice, in which case this would be flip 1 and this would be flip 2. Either way, you've got 4 different outcomes in your sample space. That sample space lists all possible outcomes for 2 coin flips. We call it an organized tree diagram because it looks like branches, basically. I sketched part of a quick tree diagram for our rolling the die in that last video that we did. It would have been huge though, because my original die, the first one would be 6 different outcomes, and then off of each of those branches, I needed 6 different outcomes. If I have fewer outcomes, like tossing a coin, it's a lot easier to do this tree diagram as an organized listing of outcomes. I see that the probability of getting heads on both coins is 1 out of 4 of the outcomes, right there, both heads. The probability of tails on at least 1. Well, tails on at least 1 means I either get 1 or 2 tails. The other 3 outcomes include tails on at least 1. So remember us talking about complementary events? Heads on both coins is my event E. Tails on at least 1 is the complement. Because if I add together E and the complement of E, I get the entire sample space. I get 1. My probability is 1. That would be a better way to put it. Let's do that. E plus E complement, the complement of the event, is equal to the sample space. Or I could say the probability of E plus the probability of the complement is equal to 1. It's equal to everything. Let's think about what happens if we add a third coin toss. Well, I would start just like I did with these 2 coins, but then now I add a third set of branches. So from each of these 4 outcomes, there are 2 more branches, and 4 times 2 is 8. So now there are 8 possible outcomes in my sample space. If you're looking to figure out how many outcomes there are, think about arranging them in order. I have 2 outcomes for the first toss, 2 outcomes for the second toss, and 2 outcomes for the third toss. That's a total of 8 possible outcomes in my sample space. So we did our tree diagram to represent our 3 coin tosses. This would be first, second, and third coin toss. And then I did an organized list. These are the outcomes represented by that tree diagram. Heads, 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 tails, heads, tails, heads, etc. It can be easier to go ahead and look at this organized list than look at the tree diagram until you're getting used to them, quite honestly. But it's a lot easier to make the tree diagram than it is to consider every possibility trying to create the organized list without the tree diagram. Okay, make sure that you answer D, those probabilities, reading very closely what it's asking you for. For example, exactly 2 coins versus at least 2 coins. If I have heads on exactly 2, then I'm looking for just the listings that have 2 H's. If I'm looking for heads on at least 2 coins, then I can have just 1 H or 2 H's. Exactly 2 heads in a row is another thing altogether. So here are my probabilities, 3/8, 4/8, and 2/8. Make sure you can find those. Notice that we didn't reduce because right now we want to compare things with a common denominator. When you're done with this, let's look at the next page. Okay, so now instead of tossing a coin, we've got colored blocks. There are colored blocks on the material cards. You can do slips of paper that represent colored blocks. Or you can just work with the tree diagrams. It totally depends on whether or not you need manipulatives to work with. But you have a set of two blue blocks, one red and one yellow. So you have a total of 4 blocks in all. You're going to draw a block from the pile, look at its color, and return it. This is important, with replacement. That means even though I'm doing 2 draws, I have the same 4 blocks to choose from for both draws. I set up an organized tree diagram. This is my first draw. I can get blue, blue, red, or yellow because I've got 2 blue blocks. This represents the second draw. If I drew a blue block the first time, I put it back. So I have those same 4 options for my second draw. So these are the possible outcomes. Since I have 4 ways to choose the first block and 4 ways to choose the second block, I have a total of 16 possible outcomes. That's an arrow, sorry. I have a total of 16 possible outcomes in my sample space. And I've got them listed out here. Yeah, okay. So I have my tree diagram and I have my organized list of my sample space with 16 outcomes. Once you've done that, come back and answer these 3 probability questions in part C, paying very close attention to what you're being asked. At least one, if I'm doing 2 draws, mean I could get 2 or 1 blue block and it counts. 12 out of 16 of those outcomes has at least 1 blue block drawn. Exactly 2 blocks of the same color, which means that the first and second draw, I drew both blue or both red or both yellow. Well, there are 6 different ways that can happen. And then finally, exactly 1 blue and 1 yellow. So I could have gotten blue on the first draw and yellow on the second, or yellow on the first draw and blue on the second. I automatically know for this one, I don't even need to look here. Because if I drew red on this first draw, it can't fit this situation. None of these 3 events are complementary events. None of these 3 has a complement that we have been asked to find. The complement of this first event, at least 1 blue, would be no blue blocks. If I did that, if this is E, the probability of the complement would be no blue. What would be the probability of the complement? Well, if at least 1 blue is 12 out of the 16, there are 4 ways to get no blue blocks. Okay, we're going to look at number 3. This was with replacement. Both draws, I had 4 blocks to choose from. Number 3, however, is drawing without replacement. I'm still drawing twice, but if I look at the number of blocks, the first time there are 4 different blocks I can draw. But that second time, I've already picked one and I didn't put it back, so there's only 3 left, which means I only have 12 possible outcomes in my sample space. And it changes what my tree diagram looks like. It's not quite as big, because if I already drew one of these blue blocks, I only have 1 left. If I drew the red block, I didn't put it back, so I don't have red to choose from. If I drew the yellow, I didn't put it back, so I don't have a yellow to choose from for the second draw. Make sure when you're looking at these problems, you pay attention to whether it says with or without replacement. Answer these probability questions, and then we'll look at the next page. I actually nearly asked, do you have any questions before we move on? I'm still not used to this talking to myself thing. Okay, so let's look at the third page for this activity. Yeah, okay. I'm going to add a couple of problems at the bottom, but we will just, we'll talk through what it has for you. This page introduces the concept of the fundamental counting property. I've already kind of started showing you that because I was showing you how to figure out how many different outcomes you can expect in the sample space. That's what number 4 walks you through. How you can figure out how many different outcomes there will be in the sample space. Part C gives us a definition for the fundamental counting property. If an event A can occur R ways, for each of these R ways, B can occur in S ways, then those two events can occur in R times S ways. So for example, if I'm rolling 2 dice, there are 6 outcomes on the first die, 6 outcomes in the second die, for 36 total outcomes in our sample space. If I'm going to roll a die and then flip a coin, 6 outcomes on the die, 2 outcomes on the coin, for a total of 12 outcomes in my sample space. If I look at this spinner, if I'm going to spin the spinner and then roll a die, well, there are 4 outcomes on my spinner, 6 outcomes on the die. If I pull a block from a set with 5 blocks and then spin the spinner, I have 20 possible outcomes in my sample space. And then I have a couple of questions for you down here. What if you're choosing an outfit? What if you're asked to choose an outfit and you packed for a trip? Right now, nobody's taking trips, but let's say we finally get the shelter in place order lifted and we all want to go take a trip. You packed 5 shirts, 3 pairs of pants, and 2 pairs of shoes, and they will all go together. How many possible outfits do you have? Well, you've got 30 possibilities because 5 times 3 times 2 is 30. What if you're making a password to something, and your password is going to be 5 characters long, and it's going to include 2 letters, 3 numbers with no repetitions? Well, to figure out how many possibilities there are for this password, you're first going to say, okay, I need 5 characters for my password. So I have 5 blanks to fill in. The first 2 are going to be letters. There are 26 letters in our alphabet. But once I've picked one, because there's no repetitions, there's only 25 letters left to choose from. For example, let's say I pick that my password's going to start with C because that's the first letter of my last name. Well, if I use C for this spot, I can't use C here. I only have 25 letters left to choose from. The last 3 blanks are going to be filled in with numbers, with digits. How many digits are there? Look at your phone or look at your calculator. You actually have, don't say 9 because a single digit goes up to 9, but don't forget about 0. Because of 0, you have 10 digits. 3, 6, 9, 10 different digits to choose from. So I get to pick a number out of those 10 digits. Let's say I pick a 5. Well, I can't pick 5 next time because it's no repetitions. So now I only have 9 digits to choose from. And let's say I pick a 0. Well, now I only have 8 digits to choose from. So to figure out how many different combinations of passwords I can come up with to match that, I multiply all of those together and get 468,000 options. Okay, I'm going to switch my pages. We're going to look at the next activity manual. Okay, this next activity manual, activity from 11.2, is more tree diagrams, but now we are going to do weighted tree diagrams or probability tree diagrams. Consider the experiment where we were drawing blocks. We can come up with this tree diagram here if I just did one draw, or I could represent it with weighted branches. So that instead of 2 branches for my 2 separate blue blocks, I just draw 1 branch for blue, 1 branch for red, and 1 branch for yellow. Then I show how how each of those is weighted comparatively. Because I have 4 blocks total, one of them is yellow, one of them is red, and 2 of them are blue. 2/4 reduces to 1/2. These are how the probabilities of drawing each color. So this allows me to look at the probability without having as many branches. So basically I'm cleaning up my tree diagrams, making them a little more efficient. Now let's consider where we drew 2 different blocks. This is the tree diagram that we created where we had 2 blue blocks, a red and a yellow. We replaced with replacement. So the next draw, so this is draw 1 and this is draw 2. So for the next draw, I still have 2 blue, 1 red, and 1 yellow every single time. I can make this a more efficient tree diagram by marking the probabilities on each branch. This has given me my first draw with the probabilities marked. So this is draw 1, and we need to show draw 2. Since I'm marking probabilities, I don't have to repeat blue. I can just draw 1 blue branch from each of these. So from blue, I could have blue, red, or yellow. From red, after I draw red first, I can have blue, red, or yellow. And if I draw yellow first, I could draw my second draw could be blue, red, or yellow. Now this is with replacement, which means the probabilities are not going to change from the first draw to the second. So the blue branch still contains half the blocks available, 2 out of 4. 1/4 of them are red and 1/4 of them are yellow. So I can calculate the probability of each set of draws. And then I can go back and look at them to see what the probability, add up the probabilities of the different compound events. Okay, so let's look. 1/2 times 1/2 is a 4th. So that's the probability of this first outcome in my sample space, blue, blue. What about blue, red? Well, 1/2 times a 4th is an 1/8. And 1/2 times a 4th is an 1/8. So the probability of this outcome is 1/4. The probability of this next outcome is 1/8. The probability of this third outcome is also 1/8. All right, moving to the next branch, notice that instead of a 1/2 on the first draw, the probability of drawing red on the first draw is 1/4. So I have a 4th times a 1/2 is an 1/8. A 4th times a 4th is a 16th. That's both of those branches. And what happens with red in the first draw looks exactly the same with what happens with yellow at the first draw because those probabilities are the same. A 4th times a 1/2 is an 1/8. A 4th times a 4th is a 16th for both of those. If I make these all a denominator of 16, add up all of these probabilities, I get 16 out of 16 or 1 because that's every probability in my sample space. Okay, using this outcome tree diagram, you can see that red, red is one outcome. It can only happen one way. Red on the first draw, red on the second draw is right here. That's the only way that can happen. The probability of that happening is 1 out of 16. All right, let's look at the next page. This tells you that what we have learned is that multiplicative property of probability. Multiplicative property of probability. When we added the probabilities in the bottom row, we found that the sum is 1, and it makes sense because though all possibilities were included. Okay. Another property of probability can be useful when you want to compute the probability of an event with more than one outcome. We're going to do this again. We want the probability of drawing a blue and red block in any order. So we want to think about the paths that contain both blue and red. So if I'm looking for a blue and red block in any order, I'm not looking at this, right? Because that would be yellow first, so I'm not going to get both a blue and a red. I'm only considering these three for the first draw, and then I don't consider where I got yellows. Notice that this has moved us back to representing every block with its own branch. Let's go and look at what we had before instead. It says using this probability tree diagram, you can see there are two outcome paths that have a blue block and a red block. Fill in the probabilities for these two outcomes. So blue and red here are here and here, right? We've got blue and red here, blue and red here, right here and right there. So this is a half time, oh, not blue and blue, blue and red. I'm so sorry. Only two outcomes. That's right. Let me fix this. I can color code it and fix it. So if I do blue and red, red and blue, those are the only two paths that I'm interested in. That gets me both colors. I either draw blue first and red second, or red first and blue second. Well, the probability of this pathway is 1/8 because half times a fourth. The probability of this pathway is 1/8, a fourth times a half. If I add those two together, I get a probability of 2/8, which is the same thing as 1/4. It's just a simplified way of looking at it. All right, using this tree diagram, which I have colored up and marked up. You can, if you need to, you can print you a new one. You can reuse yours however you want to use it. I want you to use this tree diagram and that additive property of probability that we just did, the additive property of probability. So we used our multiplicative property to get the 1/8. And then we used our additive property that if there are two different ways this outcome can happen, I can multiply to get each of those individual outcome probabilities and then add them together. Okay, find the probability of drawing at least one blue block and then drawing two blocks of the same color. So at least one blue block means I have one or two blues. So the only things I'm not going to look at would be red, red, and yellow, yellow. Otherwise, I have at least one of those blocks being blue. Oh, I can't look at red, yellow, red as well. Thank you. Okay, finally, after that one, drawing two blocks of the same color. So that would be both blue, both draws yellow, or both draws red. So I have three possibilities for that one. So if I'm looking at least one blue block, this has a blue block, so that is a half and a half is a fourth. So there is that 1/4. And this one has at least one blue, so a half and a fourth is an 1/8. So this one, and then this one as well is going to be another 1/8. And over here, at least one blue is just going to be this pathway. So a fourth and a half is an 1/8. And over here, at least one blue is going to be this pathway. So that is another 1/8. There's 5 different ways to get that with our probability tree diagram. If I get a common denominator and add that all up, I have 6/8, which simplifies to 3/4. What's the probability of getting two of the same color? Well, I could get both blue right here. That's a 1/4. Or I could get both red right here. And that is a 1/4 times a 1/4 is a 1/16. Or I could get both yellow draws right here. A 1/4 and a 1/4 is a 1/16 again. And if I add these three together with common denominators, I get 6/16, which reduces to 3/8. The probability of drawing 2 blocks of the same color is 3/8, or 6 out of 16 outcomes in the sample space. All right, number 3 wants us to do a new probability tree diagram based on what we've learned from the first 2 examples. This time we have another set of givens. We have another experiment. We're going to randomly draw 2 blocks without replacement, which means I don't put it back. So no replacement. My set this time includes 3 green, 1 white, and 2 orange. So I'm starting with 6 blocks for the first draw. I only have 5 blocks for the second draw because I'm not using replacement. All right, let's set up our probability tree diagram. We only have 3 different colors. We're not going to draw, we have n equals 6. We have 6 blocks. But we're not going to do 6 different branches because that just gets crazy. We only have 3 different colors, so we only need 3 different branches. So that's what we're going to do here. We're going to do 3 different branches. Our blocks are green, white, and orange. Now for our first draw, we have 3/6 are green. You have an option. You can go ahead and reduce and do 1/2 here for my 3/6. But I've discovered that it's easier for me to keep my denominators the same so that when I get to the end, I can simplify. When I start adding things together, it's easier and then I can simplify at the end. So I'm going to go ahead and represent green as 3 out of 6 instead of 1/2. I only have 1 white block, so that's 1/6. And I have 2 orange blocks. And go ahead and check. 3 plus 1 plus 2 is 6/6. So we have every possibility represented. Okay, we get a second draw. If I draw a green block on the first draw and I don't replace it, I still have 2 left. So on this second draw, I still have green, white, and orange available to me here. If I draw the white block, that is the only white block. So there aren't any more. I only have green or orange for my second draw there. If I draw an orange block and don't put it back, I still have 1. So I still have all 3 color choices, green, white, orange, there. Now let's write in our probabilities. Remember for this draw, the second draw, I only have 5 blocks. I drew a green one, so there are 2/5 of the blocks left that are green. 1/5 of them is white, and 2/5 of them are orange. I only have 5 blocks left to choose from. I took away one of the 3 green blocks. Let's look at the middle branch. If I drew the white block and didn't put it back, I still have 5 blocks total. 3 of them are green and 2 of them are orange. If I drew one of my 2 orange blocks and didn't put it back, there's still 1 of them left, as well as 3 green blocks and 2 white blocks. Go ahead and calculate the probabilities of each branch and write them down here below. Leave your denominator as 30. Once you get all of those calculated, and if you're not ready yet, pause me. I messed up here. Help me fix it. I ended up with 6. This should be 1/5. I only ever had 1 white block, which means that this is just 2. And that's why we do what I was about to say. When you finish, add up all of those numerators and make sure they add to 30 so that you can kind of double check your arithmetic and make sure you did the multiplication correctly. Now this next part, answering these 3 questions, this is why we kept our denominator 30. What's the probability of drawing exactly 2 green blocks? Well, exactly 2 green blocks means I draw green on the first draw and the second draw. So I'm only interested in looking at this one, and then I'm really only interested in just this one pathway. Well, the probability of that is 6 out of 30. Here I can reduce and get 1/5. I can leave it 6/30 or 1/5 depending on what I'm asked for. What's the probability of getting no green blocks? Well, if I'm doing no green blocks, I'm not looking at this at all because here I drew a green. I'm looking at these two, and then I don't include where I draw a green there. So no green blocks would be this one, white and orange. That's a probability of 2/30, or orange-white, which is another 2/30, or orange-orange, which is 2/30, which gives me 6/30 again, another 1/5. And then the final question I'm asked, what's the probability of drawing 2 blocks of different colors? So not green-green, not orange-orange. I can't do white-white. So I just need to figure out the probability of drawing 2 blocks of different colors. You guys figure that out and see what you get, and then start back the video. You should have gotten 11/15, which would be the same thing as 22/30. You had an option. You could either find each of the pathways that have blocks of different colors, or you could have said, you know what, the complement of that would be 2 blocks of the same color. Well, 2 blocks of the same color would either have to be 2 green blocks, which is 6/30, or 2 orange blocks, which would be 2/30. This would be the complement of the event I was asked for, a total of 8/30. And if I take my total set of probabilities and subtract the probability of the complement, I get the probability of the event itself. So 8/30, 1 minus 8/30 gives me that 22/30. And this way I only had to calculate 2 probabilities instead of all of the others.